Hi, this is Dr. Goldstein, and I am going to be describing what is called set notation. So, set notation is a formal way to describe a set, and in our case, we are going to be talking about how to describe sets of numbers. So, here is the format that you'll typically see set notation in. You have first the name of your set, which for this example, I will call my set S, and then your definition begins with an equal sign, and your set begins with a curly bracket. Now, I'm going to call my elements X. In the examples that follow, you don't have to. So you name your elements, and then you have this symbol here that means in. So this symbol here means in. And then the category that X has to belong to. I have a vertical bar, and then followed by that, I have some condition that X has to satisfy. And then I end my definition of my set S with a curly bracket. So once again, a little bit of description of what some of these symbols mean. So this vertical bar that I drew here actually stands for the words such that. So if I were going to read this definition one more time from start to finish, I define the set S to be the set of all X in category such that some condition that X must satisfy. So one way to think of the two different parts of this definition, this first part here is where X comes from. And the second part of the definition is what needs to be true about X. So anytime you are trying to determine whether an element is in your set, you look at the second half of the definition, the condition that X must satisfy, and you say, okay, I need to satisfy that condition. So now for a bunch of examples. So here's our first example. My set is named A, and it's defined to be all X in this bold R here, means the set of real numbers. So I am talking about all real numbers such that when I add 5 to them, I get 3. And you can look at that equation and you can say, oh, hey, I know what that equation is telling me. And if you take that equation and you just solve it, if you subtract 5 from both sides of that equation, you get that X is equal to -2. So in other words, what this set definition is telling us is that we just have the real number that's -2. So our original definition of A is a little bit clunky. I really could just say, okay, A is the set containing -2. So A is the set containing just the number -2. Okay, another example. So our set B now is defined to be R in this bold Q. So I told you before, I don't have to use the element X to name the elements of my set. I can use whatever I want, and in this case, I'm calling my elements R. And what this bold Q is this is a set of rational numbers And if that sounds scary, it's just fractions. But what I've done is I've picked the letter R for my element so that when I look at it, I say, oh, R is rational. This is pretty typical. You want to name your elements so that they make sense. And what I'm doing here is I'm defining my set to just consist of those rational numbers that are integers. So what I could do with my last set was actually just write down everything that was in it. With this set, I can't do that, but I can write down a description so that I can look at and just know exactly what's in my set. So this is an infinite set because it contains all of the integers. And if I wanted to list all of the integers, I couldn't. But what I can do instead is write enough of them that I get a sense for the overall pattern. So this is one way of writing down this set of all integers. Another way of writing this down is just with this bold symbol Z. And it's possible that you've seen this before, but what this symbol really means is just the set of all integers. So again, the first way of writing down the set is fine. It's a little bit clunky. There's an easier way of writing down this set. Okay, let's see another example. So example 3, I'll read this through from the beginning. So the set C is defined to be all n in Z. So remember that stands for the set of all integers. So n in Z such that n is equal to 2 times k for some k in Z. So let's unpack this. What this first part here says is that n is an integer. So n has to be a whole number such that n is twice some other integer. N is twice some other integer. And it's very important that I've used a different letter for my other integer, because n is reserved. N is my general element of my set, and so if I wrote n equals 2 times n, well, there aren't very many numbers that are twice themselves, really only 0. So you need a different letter. Okay, so that is just a notational detail. Let's think a bit more about this set, and if I think about what numbers are twice, what integers are twice some other integer, these are precisely the even integers. So another way of describing my set is the set of integers that are even. And again, I can't write all of these down explicitly because there are infinitely many of them, but if I wanted to write a list that'll give me an idea of what elements are in here, maybe I'll start with -6, and then go to -4, and then -2, and then 0, 2, 4, 6, 8. This list is long enough that it suggests a pattern that I follow, and so if you looked at that list and I asked you what elements are is that list describing, you'd say, oh, those are all of the even whole numbers. Great. Okay, another example. This one's a little bit more complicated. So my set D is defined to be those real numbers, x, such that when I square them, they are less than or equal to 9. And this one, you might have to think about what exactly that means. We'll be doing a lot more like this in class, but what this means, basically, x has to be less than or equal to 3 in order to square to be 9. And now this is the part that people tend to get wrong. X doesn't have to be greater than or equal to 0. It has to be greater than or equal to -3. 3 in order to square to be less than or equal to 9, because all of the negative numbers, when you square them, they become positive. And so I can have stuff that's between -3 and 0, but I cannot have anything less than -3. For example, if I take -4 and I square it, it'll be 16. That is too big. So this is another way of describing this set that maybe is a little bit more explicit than the original definition. Now, the last thing I want to do is introduce a little bit more notation for you. So I can draw this set on the real number line. So this is a graphical representation. The real number line is just a line, and I can put some sample points on there. 1, 2, and 3. And then the points that I am talking about for this set is everything between -3 and 3. So I draw closed dots at -3 and 3. And so this is my set here. This set D graphically looks like that on the real number line. Another notation that is very common is what's called interval notation. And it is a much shorter way of describing sets of real numbers. If I wanted to describe this set in interval notation, I would use a square bracket with -3, 3, and then another square bracket. And the reason why I'm using square brackets is to show that this set includes the endpoints. So I'm going to give you a couple more examples using all 3 of these different ways of representing sets, and that is the last thing that we're going to do. So, for example, if in set notation I wrote down the set X in R such that 0 is less than or equal to X is less than or equal to 2, on the real number line, I can draw that with a closed dot at 0 and a closed dot at 2, and I would connect those. And in interval notation, I would write that with closed brackets 0 to 2. Another example, if in set notation I write down the set X in R such that -3 is less than X is less than 1, this set does not include the endpoints -3 and 1, and so what I'm going to do instead is draw an open hole at -3 and 1 and connect those. So again, that's a visual representation of that set. And then in interval notation, to not include the endpoints, we use, whoops, I got those backwards. To not include the endpoints, you use open parentheses. So from -3 to 1, and you use parentheses instead of brackets. Another example, so if I have X in the set of real numbers such that -4 is less than X, which is less than or equal to, let's say, 1.5. So I don't want to include -4, so I'll draw an open hole there. And then I do want to include 1.5, so I will draw a closed hole there. And then I connect those. I want everything in between them. In interval notation, I would have a parentheses for -4 and a square bracket for the closed endpoint for 1.5. Okay, 2 more examples. So let's look at two infinite intervals. What if I had real numbers that are greater than -2? So on my number line, if I want to be greater than -2, I want an open hole because I'm not including that. Then I want everything bigger than that. And so what I do is I draw an arrow going all the way to the right, and that means include everything that's there. In interval notation, I start at -2, and I go all the way off to infinity. Last example, if I have all real numbers that are less than or equal to 1, again, on my number line, I have a closed hole at 1, and I want everything to the left of that. That was a little on the sloppy side. Let's try that again. There we go. And now for interval notation, the way that I write this is I have everything from -infinity to 1 with a square bracket at 1. One thing to notice is that you never use a square bracket with infinity. The reason for this is because this is just a symbol that really means that my set just continues forever. Infinity is not a number. Your set can never include infinity. Your set only has numbers in it. So all that notation is telling you is that your set just goes on forever. In the fourth example, what we're talking about is your set continues on forever to the right. It gets infinitely bigger. And in the last example, your set continues infinitely on to the left. Your elements can be as small as you want them to be.